So, welcome back to our next topic, that is the semiconductors. Okay, semiconductors, as we all know, because this is the thing which we are commonly using in our day-to-day life basis, and also like semiconductors are those which we have studied detailed your in our higher secondary schools and like the introduction of the first module itself. So anyway, I am brushing those things once again. Like semiconductors are those material whose conductivity lies between those of conductors and non-conductors. Conductors, you know, like metals, and non-conductors, which is likely ceramics and some polymers. So here, like semiconductors can be either some pure elements like silicon or germanium, or it can be a compounds also like gallium arsenide and cadmium selenide. Okay, and here actually what we will do is that we will just put some impurities into it, which is known as, that process is known as doping, where the impurities are added into this pure semiconductors. Then that will cause a large change in the conductivity of the material. Okay, so due to this, their role here in this fabrication of electronic device, semiconductors are like are an important part of our life nowadays. Next topic is the energy gap in the solids. Okay, like metals can be materials can be classified on basis of the energy gap. Energy gap is the space between the conduction and the valence band. Okay, valence band is consisting of the valence electrons of any atom, and the band that is above the valence band, and that is empty at 0 Kelvin, is known as conduction band. Okay, whenever there's a temperature will be there, the electrons will just excite to higher level. Okay, for insulators we can see that the band gap is very much high. That means it's electrons, it's hard for them to jump to this conduction band. Whereas for the conductors it is just almost negligible. The conduction band and valence band are almost lies just one above each. Whereas for semiconductors we can see here is a medium type of gap exhibit. So there's a chance for this to just jump into here and like act as a conductor, or else keep here and behave as an insulator. So that's why the semiconductors which comes in between that of conductors and insulators. The conduction takes place whenever an electron jumps from the valence band to a conduction band, and the gap between these two bands is forbidden energy gap. So the jumping of the electrons can happen in two ways. The first case, like as we have mentioned before, it will just gather energy from the externally applied field, and just it will jump to the another another level. So this is like monovalent metals. We can like copper, silver and gold, and trivalent metals like aluminum. But in the second case, actually what we can say is that like the conduction band just overlap with the valence band. So actually in effect there is not that much forbidden gap. So divalent metals like magnesium all behaves in this way. So now we can quantify that energy gap. So those materials which have this energy gap, which is of about 2 to 3 electron volt or lesser, are called semiconductors, and those with the gap which is more than 3 electron volt are known as the insulator. Here we can say it's an insulator, whereas this one is a semiconductor. So coming to the periodic table, like the fourth column in the periodic table, the electrons in the outermost orbit are even in number as in the divalent metals. So here like carbon, silicon, germanium, tin, lead. So here we can see the energy gaps. Energy gaps like continuously decreasing. Okay, from carbon to bottom. So this is the fourth column, 4A of the periodic table, which I am discussing. So all the students should clear the check the phosphorus symbol as B. Okay. So why elements from third and fifth group? So the reason behind using dopants, because we are selecting the dopants from third and fifth group, uh, is to have a similar sized atom, which I discussed before. So as the pure semiconductor. So both silicon and germanium atoms belong to the fourth group in the periodic table. Okay, here. Hence, the choice of dopants from the third and fifth group is more viable. This ensures the size of the atom is not very different from the fourth group. Therefore, trivalent and pentavalent choices we are selecting. Okay, the dopant give rise to two types of semiconductors as follows, like N-type and P-type semiconductors. So the extrinsic semiconductor, N-type semiconductor. So here now let us see the N-type, how it will come. When the silicon or germanium doped with a pentavalent atom, okay, see that it is pentavalent from the fifth group. It occupies the position of an atom in the crystal lattice of the silicon. So here what happens is that the four of the electrons of pentavalent atom bond with the four neighboring silicon atom. Okay, silicon atom, four atoms are just join with four atoms of the silicon. Okay, so what will happen here? And the fifth one actually just weakly bonded to the parent atom. As a result of this, the ionization energy required to set the fifth electron is very less, and the electron become free to move in the lattice of the semiconductor. This is what happening. So this will carry, this is responsible for the conduction, this electron. In this way the conduction happens. So such a kind of semiconductors are known as N-type semiconductors. The fifth electron actually cannot take part in the discrete covalent bonding, which is shown here. So it's loosely bounded here, and the excitation of the fifth electron to the conduction band, okay, just above one, takes place much more readily than excitation from the valence band of the silicon crystal. So the energy level of the fifth electron is called the donor level, which is very much critical. So now next is the so here the ionization energy is given, shown here. Okay, so the N type and this is the P type. So as compared to the energy gap, the ionization of an impurity atom is very small. Means the ionization energy here, in the sense that how difficult it is to remove an electron from atom. So for impurity atom, this ionization energy is much lesser. So that's the important part which we need to check here. Okay. So at room temperature, a large fraction of the donor level electrons are excited into this conduction band, and the fraction is much larger than the fraction of electron excited due to the intrinsic process that's from the valence band. So this condition drastically reduces the number of holes in the N-type semiconductor. The electrons in the conduction band become the major charge carriers. So this is the critical part here. The major charge carriers in N-type semiconductors are the electrons only. So now moving to the P-type. So here what will happen is that a tetravalent like silicon or germanium is doped with a trivalent impurity here. Okay, the element from the third column, that is aluminum, boron, indium, etc. Here the dopant atom has one less electron. So here, like while making covalent bond, actually here one thing will be missing. That's one electron is less here than the surrounding atoms of silicon or germanium. So this the fourth atom of the tetravalent atom is free here, and a hole or a vacancy is generated in the trivalent atom. So in such material, the hole are the charge carriers, and such semiconductors are known as p-type semiconductors. So here aluminum has 3 electrons in the outer orbit, while substituting for silicon in the crystals. Like it needs an extra electron to complete the tetrahedral arrangement of the bond. So here, like it will take from nearby. So like that, the holes will move and it will carry the charge. So here, an extra electron will be hired from the neighboring silicon atoms. So in this way, the holes will just move, propagate, and it will carry the charges. Okay. At 0 Kelvin, the holes remain bound to the impurity atom, so you need to take care of this one. So as the temperature is raised, the holes break away from the impurity atoms due to the thermal excitation and become available for the conduction. So here the bond hole levels are called acceptor levels. So aluminum accepts an electron, so it's called acceptor levels, and are just above the valence band. So that's all. This is the assignment which you need to do. That's all for this video. Thank you for your attention.